Ever find yourself hitting save and wondering, where does all that data actually go? It just disappears into the digital ether. Well, today we're doing a deep dive into that very ether, into the world of database systems.
Yeah, it's kind of amazing when you stop to think about it. All that information just lurking beneath the surface of our digital lives.
Right. And we've got some great material to guide our exploration today. Excerpts from Database Systems, the complete book. That's like the Bible of database systems, right?
Pretty much. It's a comprehensive look at how these systems are designed, built, and most importantly, how they actually work.
Perfect for a deep dive. And we've also got some research papers on database theory to add some extra context, like the Lowell database self-assessment. So should we jump right in?
Let's do it.
Okay, so when we talk about databases, we need to start with how data is structured, right? I mean, we can't just have a digital free-for-all.
Absolutely. The database systems book calls the relational model the blueprint of most databases. Imagine like a really meticulously organized spreadsheet with rows and columns neatly storing information that's the essence of the relational model.
Okay, so like a digital filing cabinet. Everything in its place.
Exactly. And this model has been incredibly successful, forming the foundation of countless applications we use every day. But
there's always a but, right?
Yeah.
What happens when the information we need to store isn't so neat and tidy? Like trying to cram a bunch of oddly shaped toys into a perfectly square box?
Mm-hmm.
It doesn't quite work.
That's a great analogy, and it highlights the limitations of the relational model. While it excels at handling structured data like numbers and names, it can struggle with more complex, messier information. Think about trying to represent all the nuances of a family photo album in that rigid table format. It just doesn't quite work.
Yeah, I can see that. So how do we move beyond these limitations? Our source material hints at alternatives like object-oriented and semi-structured data models. Can you shed some light on those? They sound kind of abstract.
They are a bit more abstract, but also much more flexible. Instead of forcing everything into tables, the object-oriented approach uses objects with inherent properties and behaviors. For instance, imagine a music database where each instrument is an object. It could have attributes like brand and tuning, but also methods like play sample sound.
Okay, that's cool. So instead of just static data points, you've got these dynamic objects that can actually do things.
Exactly. And semi-structured data takes this flexibility even further. Think of it like a network of interconnected information constantly evolving and adapting.
So less like a filing cabinet and more like a living, breathing ecosystem of data.
Exactly. Instead of being confined by a rigid schema, semi-structured data uses tags and attributes to establish relationships between different pieces of information. This makes it ideal for things like social media feeds, where connections are constantly forming and shifting.
It's fascinating how database systems are evolving to keep pace with our increasingly complex digital interactions. But speaking of complexity, let's delve into a concept that can sometimes trip people up. Dangling tuples. I'll admit, that one sounds a little intimidating.
It sounds scarier than it is, I promise. Imagine you're deleting a movie from a database, but the director's record, which still references that deleted movie, remains. That lingering reference is a dangling tuple.
So it's like a digital ghost, a reference to something that no longer exists. That sounds like it could cause problems.
It could, but thankfully, database systems have mechanisms to handle these remnants. Database systems explains that integrity constraints and referential integrity rules help maintain order and prevent inconsistencies that dangling tuples could introduce.
Phew, that's reassuring. So the system has safeguards in place to prevent these digital ghosts from wreaking havoc.
Precisely. It's all about maintaining the integrity of the data.
Makes sense. Okay, so we've talked about different ways to structure data, but now I'm curious about the nitty-gritty of data storage. Like when I hit save, what's actually happening behind the scenes? Where does that information go? Is it just magic?
Well, it can feel like magic, but it's actually a fascinating dance of attributes, tuples, and schemas. Let's break it down. That new entry you're saving is a tuple, a row, and a database table. Each piece of information within that entry, like the title, author, or date, is an attribute. And the stage on which this data ballet plays out is the schema, the blueprint that defines the structure of your database and the type of data it can hold.
Okay, I think I'm getting it. So the schema sets the stage, the tuple of the dancers, and the attributes are their costumes and movements.
I like that. A data ballet. And like any good performance, there must be rules to ensure everything runs smoothly.
And I'm guessing those rules are what keep our data safe and sound. Speaking of which, we've got to talk about ACD properties. It sounds a bit chemical, but I have a feeling it's crucial.
Absolutely. Those properties, atomicity, consistency, isolation, and durability, are fundamental to maintaining database reliability. They ensure that transactions, like online purchases or bank transfers, are processed reliably and completely. Imagine for a moment that you're booking a flight online.
Holding on to my digital boarding pass.
With ACD properties in place, either the entire transaction completes successfully, your seat is reserved, payment goes through, confirmation arrives, or it's as if nothing ever happened. No phantom bookings, no disappearing funds.
That's good to know because I've definitely had those "did I actually book that?" moments before. It sounds like ACD properties prevent a lot of digital headaches.
Absolutely. They're the unsung heroes of reliable data management. And when it comes to handling multiple users accessing and modifying data simultaneously, we have concurrency control. It's a bit like a well-choreographed dance, ensuring that everyone stays in sync and avoids stepping on each other's toes.
Yeah, no database mosh pits.
Exactly. We want everything to run smoothly, even with hundreds, thousands, or even millions of users interacting with the database at the same time. Now, shifting gears a bit, let's talk about data redundancy and the problem of update anomalies.
Update anomalies. Sounds ominous.
It can be. The database systems book highlights this with like a really simple example. Imagine a database storing information about movies, including the studio location for each film.
Right.
If a studio moves, you'd have to update every single movie record associated with that studio.
Oh, I see where this is going.
It's tedious and error-prone.
Definitely a recipe for disaster. So many places to introduce errors.
Exactly, and that's where database normalization comes in. Database systems describes normalization as essentially a set of design principles to minimize redundancy and ensure data consistency.
So like a set of rules for organizing data efficiently, making sure everything's in its right place.
Precisely, and one of the key concepts here is Boyce Codd Normal Form, or BCNF.
BCF, got it.
Imagine BCNF as like a set of guidelines to make sure every piece of information is stored in its most logical and efficient place. It's about eliminating unnecessary duplication and ensuring that updates can be made smoothly without creating, inconsistencies.
Like making sure every book in a library is on the correct shelf and has only one correct location, so you don't end up searching for it in multiple places.
A great analogy. Now, consider for a moment the challenge of actually finding specific information within a massive database.
Yeah, it's like trying to find a needle in a haystack.
Right. Or maybe a better analogy would be like trying to locate a single grain of sand on a beach.
Okay, that's a lot of sand. Talk about information overload.
It's a daunting task, to say the least.
For sure.
But databases have a secret weapon: indexes.
Indexes. Tell me more.
These data structures act like the Dewey Decimal System of the digital world, allowing us to quickly retrieve specific information without having to scan every single record.
So instead of combing through the entire beach, I can just check the designated section for that specific grain of sand. That's incredibly efficient.
You've got it. Our sources mention techniques like B-trees and hash tables, which are, they're incredibly efficient for searching and retrieving data. These techniques underpin the speed and responsiveness of the applications we rely on every day.
Like what? What are some examples?
Well, everything from search engines to e-commerce sites. When you type a query into Google or add an item to your cart on Amazon, these indexing techniques are working behind the scenes to make sure you get those results almost instantaneously.
Wow, I never really thought about it like that. It's amazing how much complexity is hidden beneath the surface of these seemingly simple actions.
It is remarkable. And just as important as efficient access is ensuring data integrity and recoverability.
Because things can go wrong, right?
Yeah.
Hard drives can fail, systems can crash.
Exactly. Because hardware can fail, we need strategies to safeguard against data loss.
So what happens when, say, a hard drive decides to call it quits? What then?
That's where RAID, or redundant array of independent disks, comes into play.
RAID. Another acronym to add to the list?
This one's important, though.
Okay, tell me why.
Think of RAID as like a safety net for your data. Instead of storing all your data on a single disk, RAID distributes it across multiple disks.
Okay, I'm starting to see the benefit here.
Creating backups and redundancies.
So even if one disk crashes, the data's safe.
Exactly. Even if one disk fails, the data remains accessible and can be restored.
That's reassuring.
Database systems describes how RAID levels offer varying degrees of protection and performance, depending on the specific configuration.
So it's not one size fits all. There are different levels for different needs.
Right. It's about finding the right balance between redundancy and performance for your specific use case.
Makes sense.
But the key takeaway here is that it's not just about storing information. It's about ensuring its survival. We need to think about data resilience as a core principle of database design.
Absolutely. We've talked about the importance of structure, efficiency, and now reliability. But what about the actual languages we use to communicate with databases? I mean, we can't just walk up to a database and ask it nicely for information, right?
You're right. We need a way to translate our intentions into commands that a database can understand. That's where database query languages come in.
Okay, so it's like learning the secret handshake to get into the database club.
Exactly. And SQL, or Structured Query Language, is one of the most widely used languages for this purpose.
SQL, heard of it. It's like the lingua franca of databases, right?
Pretty much. It allows us to interact with databases to extract specific data, update records, or even modify the structure of the database itself.
So SQL is like the Rosetta Stone for talking to databases.
A very apt comparison. And while SQL is incredibly powerful for working with relational databases, the rise of object-oriented and semi-structured data models has led to the development of new query languages.
Of course, because different data models would require different ways of interacting with them.
Exactly. For instance, XQuery is specifically designed to work with XML, a language for representing data in a structured, hierarchical format.
XML. Now, that one rings a bell. It's often used in web development, right?
Yes, it is. Web pages often use XML to structure and transmit data. And just as SQL allows us to work with data in tables, XQuery provides a way to navigate, search, and manipulate data stored in XML format.
So essentially, different data models require different languages to unlock their potential.
Right. It's like needing a different set of tools for different jobs.
It seems like we need a whole toolbox of languages to effectively communicate with the diverse world of databases.
That's a great way to put it. Each language serves a specific purpose, providing the tools to interact with different types of data and achieve different goals.
It's all about having the right tool for the job.
Precisely. And as the world of data continues to evolve, we can expect to see even more specialized languages emerge, each tailored to the unique demands of new data models and applications.
So it's a constantly evolving landscape. It's fascinating how these languages act as bridges between human intention and the complex inner workings of database systems.
Indeed. And as we delve deeper into this world, we begin to appreciate the intricate interplay of theory, design, and practical application that makes modern data management possible.
It's a fascinating world down here, that's for sure. So we've got all these different languages for different data models, but it seems like there are situations where you might need, like, the best of both worlds, right?
Absolutely.
Is there a way to bridge that gap? The database systems book mentions something called object relational models. Sounds like a mouthful.
Yeah, object relational databases try to do just that.
Okay.
They bring some of the flexibility of object-oriented programming into the kind of the structured world of relational databases.
With like a hybrid approach.
You got it.
Trying to combine the strengths of both.
Exactly. Imagine being able to store not just, text and number.
Right, the usual suspects.
But also like complex data structures, even images or geographic locations directly within your database tables.
Oh, that's interesting. So instead of just storing a link to an image, you could store the actual image data itself.
Exactly. Or instead of having separate fields for latitude and longitude, you could have a location field that stores a point on a map.
Okay, that makes sense.
Yeah.
Can you give me a more concrete example, maybe? Something to really bring this home.
Sure. Let's say you're building a geographic information system like Google Maps or something.
Okay, I use that all the time.
In a traditional relational database, you might have separate tables for points, lines, and polygons.
Right, the basic building blocks of maps.
Exactly. But an object relational database allows you to define a geometry data type with subtypes for each of those geometric shapes.
So it's like having a specialized data type that understands spatial data.
Precisely. This lets you store and manipulate spatial data in a way that feels much more natural and intuitive.
So it's not just about storage. It's about making the data itself more meaningful and easier to work with.
You got it.
This deep dive has really been eye-opening. It's amazing to think about all the hidden complexity behind something we use every day.
I agree. It's easy to take these systems for granted.
Totally. We've journeyed from the fundamental concepts of relational databases to this nuanced world of object relational models, explored the challenges of data integrity and recovery, and even decoded the languages we use to communicate with these systems.
And we've only scratched the surface.
Really, there's even more to it.
Oh, absolutely. The field of database systems is constantly evolving, driven by the ever-increasing volume and complexity of data in our world.
So what's next for databases? What does the future hold?
That's the million-dollar question. But one thing's for sure, as we generate more and more data, we need even more innovative ways to manage it all. We need to ensure that data is stored efficiently, accessed quickly, and used responsibly.
Data responsibility. That's a great point to end on. It's not just about the technology. It's about using it ethically and thoughtfully.
Couldn't agree more. Data has the power to shape our world, and it's up to us to make sure it's used for good.
Absolutely. Well, on that note, I think we've reached the end of our deep dive. It's been an incredible journey, and I've learned so much about the invisible world of database systems.
Me too. It's been a pleasure exploring these ideas with you.
Likewise. And to our listeners, thanks for joining us on this deep dive. We hope you've enjoyed exploring the fascinating world of database systems with us.